Our project is a comparison of traditional neural and transformer approaches to emotion labeling. Our motivation behind this is that it's difficult for machines to be able to detect the emotion from text alone, and the emotion, context, and tone of that conversation can drastically change how that is interpreted. We're going to create a model that detects the emotion behind the conversation, and this project is based on a study from Rashkin and others that did something similar. Our data comes from the Rashkin study that has 25,000 prompts describing an emotional situation. 32 emotion labels are chosen from literature that were put onto these situations. From those 32 labels, we consolidated that down to 6 emotions based on the feelings wheel from Gloria Wilcox. So in the original data, they would have had angry, annoyed, and furious, and in our new data set, those would all be classified as mad. For the text processing, we tokenized and lowercased everything first, and then we computed word embeddings with Stanford's GloVe embedding. For the support vector machine, we averaged those vectors element-wise to get a single input vector. And then for the neural network, we padded the sequence so they all have the same length.
So for our three models, we used the support vector machine on averaged word embeddings. And then we trained a bidirectional long short-term memory neural network, the architecture being on the left here. And then we also did some retraining of a BERT transformer from Google. Our support vector machine was a fairly simple model. It was just a linear kernel with relatively low regularization, and we decided on the hyperparameters from that model through cross-validation with 12 different sets of hyperparameters. Our bidirectional long short-term memory network was a little bit more complicated. So we basically fed in indices to the embedding layer, which then led to embeddings for each token, which we passed into the long short-term memory network, which went in both directions. So we had a forward and a backwards pass. And then there were two layers of that, and the output was concatenated, the final hidden layer, such that the forward and the backward layers were both included. And they were fed to a fully connected network that then reduced the number of units down to our classification size. So our BERT model was a retraining of the pre-trained uncased BERT model that was released by Google. So essentially, we appended a fully connected layer to channel the output from the transformer into our classification scheme. And then we also retrained the final pooling layer as well as the final three encoder layers of the BERT transformer. So we see the training performance for each of the neural models. So at the top, you can see this is the test F1 after each epoch of training. This is after we did all of our cross-validation, and this is just on the actual test set. And then at the bottom, we can see our loss. So one interesting observation is that the loss, the test loss for the BERT model actually increases after the first 8 epochs, even though the best F1 score was actually achieved at the 25th epoch. So we think that's likely because of a couple of factors. One of them is that our data is class imbalanced, and so it could be learning certain classifications better while also actually increasing the overall loss by assigning underrepresented labels more often. And then second of all, it could be reflecting increasing model uncertainty where the predicted values for the true class are lower, though still dominant. So our results were really as expected. The models performed better as we sort of proceeded from less sophisticated to more sophisticated. So the support vector classifier achieved about a 0.61 macro averaged F1 score. The bidirectional LSTM achieved about a 71, a 0.71. Then the BERT actually got as high as a 0.81. So the BERT did outperform the other models. It did take longer to train, but it was still in a matter of 5 to 10 minutes using a good GPU. And here are our references. Thank you very much.